Hi, good afternoon. We're Team Trust Computing, and we are presenting side channel attacks on IoT trust computing. Our team members are Arup, Spencer, myself, Xavier, and Kairul. So TrustZone is basically the virtualization of a CPU core. It allows the partition of hardware and software systems so that they can exist in one of two worlds, those worlds being secure and non-secure. You can refer to this diagram on the right. So secure and non-secure entities or worlds within a CPU core can also interact with each other, and that means calling functions or sharing information. So this is a way of securing embedded systems. An example of this would be if we have an IoT device that's accessing the internet, instead of exposing ourselves to vulnerabilities from downloading things from the internet, we're going to do that all directly from the non-secure world, so that none of our vital information or software hardware is exposed to threats. So we're looking at two chips in particular, the ARM Cortex-A and the ARM Cortex-M. So both have a secure and non-secure worlds. The difference with A is that it uses a secure monitor for context switching. Context switching is when we switch between the secure and non-secure world. So a secure monitor is essentially a piece of software which controls the interface and switching between the secure and non-secure worlds. In the case of ARM Cortex-B, we use a secure function entry points for context switching. So a secure function entry point is essentially an address in memory that holds a security attribute unit, or SAU, that dictates the security level of the function or memory that we are accessing. You can see an example of this on the right with the secure state memory map. We basically map each address to a green secure or red insecure. So the benefits of using a secure monitor over the benefits of using a secure function entry point over secure monitor is that we have faster context switching, which reduces latency, and we also have lower power consumption, since a secure monitor would take another CPU core to run. So the goals of this project are, first, to explore the setup of TrustZone M, and second, to propose a novel side channel attack on a TrustZone M enabled system.
Here are the milestones that we've completed since the statement of work presentation. First, we've acquired two Cortex-M processors, the M23 and M33 controllers that we're going to work with. And using those microcontrollers, we're able to explore the setup of TrustZone M. Provided all the software that we're going to use to run a simple program, and understanding how we are able to switch between secure and non-secure and what it's able to do. And Arup will propose a threat model that will potentially exploit TrustZone M. And here is our updated timeline for the deliverables. As you can see, what I've said earlier have been checked off as our milestones are heading towards now implementing what Arup will be discussing after I've done speaking. And we will try and find the vulnerability that we can propose in our documentation and final reports. So hopefully we'll have more updates for that coming up in our November 6th reports.
Hey guys, this is Arup, and I'm going to present the threat models, the chipset for the experimental setup, and the results. Basically, we proposed a threat model based on ARM Cortex-M 55 and M35P, because M55P has an inbuilt cache memory, instruction, and data tightly coupled memory, though M35 doesn't have the instruction and data tightly coupled memory, but it has the cache memory as well. But the problem is no vendor released any board compatible with M35P or M55. So later, we mainly focused on the processor M23 and M33. Though it doesn't have any cache, IDCM and DDCM, but the good thing is it has a DRAM. So we have changed our threat model based on the new design of M23 and M33. So we have found two boards basically. The first one is M33 and the second one is M23. Voodoo one has the TrustZone enabled, but NXP one doesn't have the TrustZone. So we have searched in the internet and found a new one which is 55869. So we have learned a lot of stuff from this exploration. So this is our first threat model. We have planned to add a cache memory by observing cache miss and cache entry delays and design our threat model. So because of the chipset availability, we have changed our threat model to that one. Based on this threat model, let's say an attacker have both secure and non-secure app running on an IoT device, and he wants to steal information from other vendors' app running on the same device. So his intention is to develop a malicious code which has the memory leaks in the secure world. Whenever he runs the code, because of the memory leaks, he can easily get the data from the other apps by overflowing the buffer. So we have planned a hard bleed attacks on IoT trust computing environment. So before going to details about our experiment, let's check the runtime M33 memory attribute map. We have exported these from the NXP LPC55S69 board during running our program. We see here, non-secure program flash memory start with the base address 10,000. Secure program flash memory start with the base address 10 millions. And the non-secure callable, which we call here a finiat table, and which is also the entry point to the secure area. Let's start with the 10 million FE000 address. Here, we have seen the secure attribute unit is called SAU, and the implementation defined attribute unit, which is called IDAU, ensures the separations of its memory footprint with the security attributes. So here, SAU is internal and IDAU is mainly external unit. So mainly defined by the silicon vendors who actually develop the main board. So based on the attribute map, the processor secure states only have access to the secure program flash memory, secure data RAM, and non-secure data RAM. And the processor non-secure states only have access to non-secure program flash memory and the non-secure data RAM. So we have set some experiments on Cortex-M23 and M33 processor. So at first on M23, we executed a secure and non-secure LED turn on and off app with the secure interface, that is secure application 1, then to VNet table, and then to secure non-secure application 1, then to VNet table, then to secure application 1. On M33, we have also executed a secure and non-secure string comparison app, which doesn't have any secure default, and we have successfully executed it. After that, we have planned some attacks on the secure applications. So which is, we tested an invalid transitions from secure to normal world. We also tested invalid entry point from normal to secure world. And there are also some attacks ongoing, which are invalid data access from normal world, invalid input parameters in entry function, invalid data access from normal world.
Here's a quick little example that our team put together just to familiarize ourselves with the environment and how we're able to run sample code from the package that was provided when we got the M23 microcontroller. This example is just an LED sample code where the project consists of both secure and non-secure, and it's able to turn on both the IO LED lights, the general IO lights, by accessing both secure and non-secure, where non-secure can call into secure's main method using the NSC state, which is the only way for it to be validated to go in and actually interact and turn on these lights. As you can see on the right, where the arrow is pointing and showing the two different lights being turned on, it's for the secure LED and the non-secure LED. And just to make sure this is a little bit more better illustrated, as you can see, I pointed out some of the output from the COM port when this is plugged into the USB ICE to the PC. You're able to look and inspect the output that's happening in the terminal if you check out the COM port. And this is what happens when you execute it, when it recognizes when you correctly link both the secure and non-secure together. It'll tell you that the non-secure is running perfectly fine and it's able to access secure with the NSC function, as you can see here, which is the only way it can access it. And it will turn and do that repeating blinking lights over and over until something interrupts it, which is usually the user externally turning it off.
For doing the test with the NXP chipset, we mainly install MCU Express ID, which is nothing but a Eclipse chipset with the NXP plugins. Here you can see that there are two projects. One is secure fault and another is non-secure fault. And these two projects are connected with the vignette table and a linker file which is generated when I build this project. So I already built that project. If I just run, it will execute the first test case. That means just comparing to a string here. So let's pause the debug point here and see the output into the terminal. You see the terminal here. This is the second test case. If we run the program, it will just show the error here because we are unable to perform the transition from the normal world, from the secure world to normal world here. So if we see the result in the terminal, so we will see. So it will not show anything. So when we just stop the program, see, it will show the error messages here, the invalid transition from secure to normal world. This is the third test case from invalid entry point from normal world to secure world. So if I just bypass the debug point, it will generate an error. We can see only the output if we just stop the program. See, there is a hard fault, invalid entry point to the secure world from normal world.
Hello everyone, my name is Khairul and I'll be presenting the comparison with related works and also our project risk and backup plans. Most of the prior works we found on ARM Cortex-M processor focused on processors M0 to M7 and they don't come with a TrustZone input. We are able to find a few recent works which have actually worked on the TrustZones in M23 and M33 processors. The first one analyzed device power issues to exploit secrets from the TrustZone. And the second one recovered architecture of black box AES engine to leak device intrinsic keys, for example, private keys from the TrustZone. So the risks associated with our projects are managing TrustZone-based processors. We actually were not able to find the two most recent processors in the market. So we had to change our attack model for what we were able to get. And the second risk is to failure to meet project timeline deadlines. We actually have a development board for each of our members. So we will be able to work in parallel and we hope that this will speed up our project work. And the third risk is we won't find a novel attack in time. So in that case, we can analyze the vulnerabilities in the trusted apps. We can see whether their implementation will leak any kind of sensitive data from the TrustZone. So these are the references we have used in our presentation. Any question?